Okay, we are live now.
Okay.
You can.
Hello all. We are pleased to invite you to the second talk in this IEEE MEMS Sensor Cluster webinar series. And this talk will feature engineer Alfred Hodea, an esteemed industry expert in MEMS and industrial automation. He was in fact nominated by IEEE Joint Nigeria chapter, and we are grateful for their valuable contribution to our speaker lineup. And a brief bio about our speaker today. He has over 17 years of experience in manufacturing and automation industry, and he is an electromechanical engineer and industrial automation specialist. So he is currently operating as a freelance technical consultant in Alfred Hodea International Limited, delivering expert industrial automation support to a range of clients. So over to engineer Alfred Hodea. Let's hear from him.
Thank you very much for the introduction. Now, I will like to come up with my screen.
Yes, yeah, sure.
Are you able to see my screen now?
Oh, no.
Not yet, sir.
Yeah, now we can see. Yes.
Okay, I think it will take 50 seconds to go.
Okay.
Yeah, the presentation not visible. Okay, now it's visible.
Yeah, now it is. Yes.
Great. Okay, so you're all welcome to the sensor design and application in advanced manufacturing process. And today we are going to discuss at length about the types of sensors. We're also going to look at the operational principles of the sensors. And we are going to see application in manufacturing this industry, as well as looking into the trends and challenges associated with using these sensors. And we will go into as well the question and answer discussion at the end of it all. So without wasting much time, we will like to go over to the next slide, which asks directly the question what sensor is all about. And for us to know, looking at the block diagram here presented, sensors are devices that detect and respond to input from the environment. And these inputs from the environment can be in the form of temperature, it can be in the form of pressure, it can be in the form of light. And what sensors does is that they just sense these physical inputs. Although they cannot by themselves work alone, they require transducers or transmitter in order to convert this detected signal into a readable signal, such as electrical signal. It could be digital, it could be visual. And sensors in a whole, the purpose of which is they allow machines and systems to take a complete care of themselves without human intervention. We are going to look at their role also in manufacturing. Sensors make it possible for machines to work without human input, like I said earlier, when it comes to playing the automation part of the role, and they detect conditions and trigger certain functions. And in real-time monitoring, the variables such as the temperature, pressure, and motions are also continuously tracked for immediate response. And they are very effective for safety and efficiencies. It helps to detect malfunction early enough and reduce human error and optimizes the process, the production process to continue. you can take a look at the benefit from this short video clip, how sensors are being used in the manufacturing industries. Here, a retroreflective sensor, for example, in this case, whereby it can be used in numbering or counting the number of cans passing through the conveyors. You can see this is done independently without human intervention. Carrying out the real-time monitoring, and it's more effective. It's giving the on signal, which goes directly to the programmable logic controllers. I pause briefly from there just to give an overview of what sensor does in industries. We go over to the classification of sensors. Sensors are being classified based on what the properties they measure. Could be they measure temperature, they measure pressure, proximity, light, vibration, flow. There are a lot of different types of it. So we look at their classification based on the properties these sensors measure. We also classify them based on the output type they offer. If the output of the sensor is analog, then we can call it, okay, it's an analog sensor. If it is a digital, we classify it also as a digital sensor. Then we also go into contact. We classify them by contact. Are the contact-based sensors that which you have a direct physical touch before they respond to an output, or non-contact sensors? These are three different ways which we classify them. And if you look at here, we have a lot of types of sensors shown here, like the air pressure sensors, humidity sensors, alcohol sensors. There are numerous types of sensors here shown. And we are not going to discuss so much into all of these kind of sensors. We are not going to talk about all of them. We will only pick some to discuss more about it, just perhaps one to dive more into it, and that has to do with pressure sensor. But before we discuss what pressure sensor is, we will like to know what pressure is. Pressure is an expression of force exerted on a surface per unit area. And we commonly measure pressure of liquid, air, and gas, among the other things. The standard unit for pressure is the Pascal, and this is equivalent to 1 Newton per meter square. Among the well-known standard for measuring pressure is bar, and PSI also, which is well known among people living in the United States. The pressure of an air, for example, in this next slide, in your vehicle tire is a great example of pressure and how it is measured. As we air the tire up, the force exerted inside the tire increases, causing the tire to inflate. And this is monitored with a pressure sensor inside the tire for most vehicle types. So, how does pressure sensor really work? Look at this next slide. You can see, in a nutshell, what it does is that it converts the pressure to a small electrical signal, which is being transmitted to the PLC via the input card of the controller. And for this same purpose, it is also called the transmitter. And the two basic types of signal used during the transmission are 4 to 20 milliamps or 0 to 5 volts, depending. Most pressure sensors function using piezoelectric effects. And that takes us to the next slide. This is when a material creates electric charge in response to stress. And the stress can be pressure, usually pressure, in this case, for pressure sensor, which can also be due to bending, it can be twisting, it can be vibrations. And the pressure sensor detects the pressure, and then it can determine the amount of pressure by measuring the amount of the electric charge directly here. And going more into what piezoelectric effect is, in 18th century, precisely 1880, it was discovered that certain crystal materials such as quartz, Rochelle salts, and many others generate electrical charge when subjected to pressure. That effect was named piezoelectricity, derived from a Greek name piezen, meaning to press. So these crystals in their natural form are integrated in the designs of pressure sensors, such that when the sensor detects a force per unit area, which is pressure, this pressure can be in the form of maybe gas, it can be in the form of liquid, it can be also in the form of mechanical stress, like I pointed before. It can be in the form of vibration. The pressure makes the piezoelectric material inside the sensor to deform slightly, causing displacement of electric charge within the crystal structure, leading to a net electric polarization. That displacement or the displaced electric charge are then seen across electrodes that are attached in the crystal, then creating a measurable voltage, which is proportional to the applied pressure, just like here shown. From the hammer here, you can find from here the hammer here. And this is the quartz. And then when force is being applied directly here, it creates electric charges, which can be seen across the connected, which is connected, and then it can be measured directly with a voltmeter or thereabout. So that we can go to the next. Sorry about my drawing. I hope I'm being heard clearly. I hope.
Yeah. Please go ahead.
Sure. Good. So going over to the next slide, we see we have three common pressure sensors or pressure that can be measured with pressure sensors in industry, commonly measured in industries. And those pressures are first gauge pressure measurements. We also carry out oftentimes absolute pressure measurements in the industry. We also carry out differential pressure measurements in the industries. And regarding the gauge pressure measurement, first of all, here we measure the reference with reference to atmospheric pressure. Atmospheric pressure, it's usually a standard of approximately 14.7 psi. And where we have a positive pressure value, then a positive pressure value means that we are measuring a value above atmospheric pressure. And value below 14.7 psi indicates that we are measuring less than atmospheric pressure. And then regarding the absolute pressure, in this case, the sensor measures pressure against vacuum. Normally, a vacuum pressure is 0 psi. So if you desire to carry out measurement of a value that is less than the atmospheric pressure, So you use this kind of pressure sensor for absolute measurement. And in practice, it dictates how much vacuum or negative pressure exists in a system normally. In industries, we use this kind of one, for example, in places like where we want to extract, like in vacuum pumps. For those in the alcoholic beverage manufacturing firm, like in filling and packaging, when we in the process of evacuating air from a returnable glass bottle or glass bottle directly, we suck all the product because the filling process doesn't have to take place alongside with air inside. So we need vacuum, and good vacuum, a negative value. So in this case, we use this kind of sensor in this application for vacuum pumps. The third type of measurement I was talking about has to do with differential pressure measurement. This one, it's clear enough in the sense that we measure the difference between two pressures, and then the reference one, as shown in the picture here, it's what is being captured. We only take measurement of two, the actual what we want to measure, and then the reference ones, then we have the value of it all. In advanced manufacturing industry, we can also look at the uses of these measurements. And that takes us to the next slide, where we have the application in boiler, for example. Here you can see just a picture indicating a boiler. Boiler is used widely in industry to provide steam to destination machines. And in this case, we can use this pressure sensor in various means. For example, you can see here, we have PS1, where we are indicating the boiler directly just to observe and view the pressure that is in the boiler itself. We also use pressure sensor in this case to indicate also the pressure. For example, if the pressure of the boiler is 12 bar, just for example, and then we are firing the boiler more without consuming what we fire. And then if the pressure is built above the required pressure inside the boiler, with the help of a pressure sensor like seen in this case now, it can send information to the programmable logic controller via the input card, informing the controller to open a safety valve, which is shown here as PRV, which is a pressure relief valve. It opens the pressure relief valve, and then with the pressure relief valve, decreases the pressure a little bit for the boiler, and then it's back to normal. This reduces accidents. So in essence, it works in the form of assisting in safety control, mitigating the risk associated with boiler or excess pressure. We also, like in the case of the third here, this third sensor here shown, it can also checkmate the volume of steam transmitted to the sent to the destination machine. Assuming the boiler is having about 8 bar, and then we are sending up to the destination machine requirement could be we say 5 bar or even a 4 bar. For example, if it is 4 or 5 bar, then with the help of this sensor, pressure sensor, we can now say to the pressure sensor, open. In addition, because it's actually not going to work alone, it's going to work alongside with other equipment such as the modulating position and modulating valve for steam. So when the pressure sensor senses steam pressure more than the required, whereas our intention is to send just about 5 bar to the destination machine. Meanwhile, the ability of the boiler it's 8 bar. Then we can tell the controller, when you see a pressure of about 8 bar, okay, what you have to do is close the modulating valve about 75% so as to reduce the pressure of steam sent to the destination machine. This is various ways which we can actually use pressure sensors in the case of a boiler like this in industry. And we can go over to the next slide. Here, the differential pressure measurement. Here, the pressure sensor are also installed to within filters, or in order to be able to check in different forms. For example, like this picture shown here, it's a direct flow of liquid. And you can see pressure sensor in this case installed in between a strainer or maybe a filter. We check the incoming pressure in this other side, and then we also check the outgoing pressure in the other side, and then we compare the pressure. When there is a very high difference in the pressure itself, then the value of the pressure it's given to the PLC, that's a programmable logic controller, via the card, and then a little programming is already done inside, whereby with the help of that program, the sensor will be able to offer information to the programmable logic controller, and then the programmable logic controller can put a stop to the machine, thereby alerting either via the HMI that there is a filter clock in between due to the pressure difference, which is too wide among them. It's either the filter in here seen between, so either it's too much, it's clogged, or the filter is completely dirty and then it has to be replaced. This application is widely used in the like cleaning system, effluent treatment plant, and many others to checkmate pressures. We also use it, for example, in checking leakages in between tanks where there is big differences in pressure. So a small programming is done from the controller side of it, and it does these checks and transmit the information to the logic controller, where alert will be sent to the HMI operator, or the technical personnel will know exactly the current condition of the filter. Then going over here, another common use of pressure sensor is a level measurement. As shown here, basically the hydrostatic pressure measured from the sensor is being used. In manufacturing industries, this is a common and effective method for measuring the level of liquids in a tank or in vessels. The key idea is that the pressure at the bottom of a liquid column is directly proportional to the height or the level of the liquid. So for those in the filling and packaging industry, can take your mind back to machines like bottle washers and tunnel pasteurizers, or even in buffer tanks. To achieve desirable result, the pressure sensor must be mounted either at the bottom of the tank or by the side, very close to the bottom. For a vented tank, pressure gauge sensors are also used, like in the case of tunnel pasteurizers and bottle washer, which I mentioned earlier. Whereas in absolute differential, pressure sensors are also used for a close pressurized tank. Or if you want to make use of this in measuring level in the tank, what you have to do is that the density or the specific gravity of the liquid itself need to be known. That is if the liquid is not water. For water, of course, is a standard that we have already for the value for water, and then we already know the value for the acceleration due to gravity, 9.8. Then the height of the tank has to be done by measuring what it is. You physically can make measurement of the height of the tank to determine it. And that is what we commonly do by scaling. In the program part of it, we say we scale the sensor to harmonize with the physical tank. So as to use it for level measurement. So like I said earlier, there are things that can affect these ones, like the density, the type of liquid you're going to use. That is, if, for example, if it is going to be caustic or if it is going to be oil. So this need to be known. Then foam or agitation may also affect the sensor reading. Put this into your mind. That can affect sensor reading. So you have to think about how you will mitigate this, maybe by filtering excess foams or thereabout. Another thing that can affect using this can be mounting errors. If not properly mounted, then there can be possibility for bubbles or height error. And remember, like I said, it must be mounted very close to the base of the vessel. Venting also, if you are using it for level measurement, you also ensure that the tank has an open end. It has a vent so as to avoid pressure build back. Okay, if you look at the next slide, you see this is just a PID drawing for a tunnel pasteurizer. And in a tunnel pasteurizer like this, from the R1H zone and down to the R1C zone, you have water in the level in the tanks. This needs to be maintained during production in industries. Same is applied to R2H to R3, R2C, and vice versa. They are recuperating each other. So in industries, we use the level sensor to ensure a stable or sustained stable and equal level in both tanks. Thereby, during production, the both pumps are running, but we want to achieve level balance in both tanks. So this is also an application of it in industry. And I will also, these are example of physical sensors. You can see example of physical sensor here used as pressure in the industry. This is a very good example. This is a deaeration tank and how sensors are being used in applied. You can see they are being connected directly with cable, which goes over to the input card and then transmit the information, like I said before, to the programmable logic controllers. So from here, the pressure, the hydrostatic nature gotten from the sensors themselves being transmitted to the programmable logic controller. The logic controller itself send and act on the information transmitted by the sensor themselves. So I go, I'm having problem a little bit with my drawings. Huh? I hope we are together.
Oh, yeah. All good.
Good. Okay. Now, I spoke about piezo electric pressure sensor. and simple designs. If you take a look at these pictures, there are examples of pressure sensors, usual pressure sensors designs. And how do they really work? Here, the pressure sensor itself is screwed in the measuring points at the process connection, right inside here. And that is the step one, how it is practically being designed. And if you go to the next one, sorry, here, we have the pressure sensor elements convert the presence pressure into an electric signal. Is directly in here, the element itself. And the next picture, the next slide shows an electronic circuit. It's a conventional electronic circuit where a conditioning circuit, I will say, like an amplifier, whereby the sensor detects the information and then passes through the amplifier. The amplifier, the tiny voltages seen from the sensor, it's being amplified by this electronic circuit here built in. And after being amplified, it goes over to the next slide. Sorry, this is being amplified and goes over, hand it over directly to these electric connectors. Usually there is a body here, a suitable case like this is just to protect it against environmental influence. And also we put into consideration different types of cases per different types of also uses. For example, the kind of sensors we are going to use in steam boiler must be able to resist high temperature, and we have to put into consideration or factor using a case that can accommodate temperature over 150 to 200 degrees Celsius. And then for such, we also can limit the use of material towards, maybe if we are using the pressure sensor for low, let's assume for just a mere cold water or for water of a room temperature, then we may not bother much about reinforcing the suitable case part of it. This is important. And then this is how it comes to the electrical connection. And after the electrical connection side of it, it is then being protected this way with a cover. So, and then just that. So here we can see the operational principle of it all. The sensors operate in various forms in terms of resistive. It measures changes in electrical resistance. That is for pressure type, like in terms of strain gauge. And then we have capacitive. That's the operational principle of which. But for today, we only spoke about piezoelectric, and subsequently we will go over to something else. But for today, we concentrated on the operational principle of pressure sensor using piezoelectric electricity. And we have also the system being integrated in different forms. For example, sensors are very good. We use in the sense that in programmable logic controller, I've mentioned that already. We apply it in SCADA monitoring. Without the help of sensors, we cannot work without with SCADA. And also we apply it in Internet of Things and many more. And then the use case example has to do with different industries. Application in automotive assembly, you have a lot of robots working alongside with sensors for effective production. In dietary industry also, this is widely used. I make mention of storage and also pasteurization conditions that are kept correct by temperature sensors, for example. This is just to show advantage of how sensors can be in industry. And then in pharmaceutical manufacturing, many more in terms of fluid flow mixing and sterilization and many more. We have level sensors like and pressure sensors like what we have discussed today. So the use cases are so huge in various industries. The trends and the innovations are varied. Presently, we have a lot of sensors that are smart sensors. There are even self-diagnostic sensors, many of which, and some have the ability to communicate directly to the controllers themselves because they are smart sensors. We have wireless technologies, a lot of which are now more available. And then the advantage is that this kind of one, they reduce the wiring cost and also they reduce complexity. Installations in remote and rotating equipment are also advantageous when it comes to wireless technology sensor application. We install some of them in rotating machines where a normal standard wired sensors cannot be possible to fit in such places. AI and predictive maintenance. These sensors are also able to predict the failure based on sensor data. They can predict their own failure. And also they help in minimizing downtime and also minimize maintenance costs. This is a lot of great advantage and the innovation in the sector of sensors. However, it goes with challenges. And among the challenges are heat, environmental factor like harsh environments, where you have a lot of heat, where you have also a lot of moisture. How to manage this poses a lot of challenge like dust and many more, because these can practically shorten the life and reliability of these sensors themselves. And secondly, another challenge, calibration and accuracy. There is always a need for every of these sensor, like the pressure sensor, what I mentioned before, to be calibrated. Usually it is a job of just being done by the technician or by the technician. Usually it is just like a span and a zero and span calibration, or what I can call maximum and minimum calibration, for you to help the sensor to know its own accuracy perfectly and to carry out their measurement perfectly. So this calibration varies per manufacturers. Most manufacturers, they offer the instructions on how you have to carry it out. Some are quite complex and some are less complex. So these pose challenges, and then you have to try to ensure you have precise reading during calibration of these sensors, because the improper data can come as a result of poor calibration of the sensors. And for the other one, when it comes to cybersecurity risk, most especially when it comes to the smart sensors, they can pose security risk. They are vulnerable to attack and security breaches. So these are also things are part of the challenges associated with sensors, with these sensors. Then in conclusion, I will say that modern manufacturing processes are really not possible without the help of sensors. It is practically not possible. This is clear and accepted. All industries, they need sensor in all sector of the industry, whether different kind of sensors. And then the process of sensor design for different measurement types and environment also differs. So we spoke already about the principle behind it. capacitive, resistive, and piezoelectric. And sensors have a lot of wide application when it comes to integrating it to programmable logic controllers, also with SCADA and Internet of Things. Then when you are selecting, or the choice of your sensor also matters a lot. So selecting the proper sensor also can help increase your efficiency and safety as well as reliability. So we can see in an overview how valid and good sensors is in industry. And I will pause for now. And like I said at the outcome, that I will stop for a Q&A. It shouldn't be just me alone talking. I will also like to hear from your side.
Uh, uh, Hi, Engineer Alfred. It was really inspiring talk. And there are quite a few questions in the chat box, and I hope you can address each one of them one by one. It would be nice to start with Mr. Armando, who asks about it is very promising approach to measure the accurate level of fuel in petrol station reservoirs, but the challenge is that they are underground, which is an issue for regular maintenance, he says. Do you have any comments to make on this?
What can you repeat once again, please? It says
It is a very promising approach to measure the accurate level of fuel in petrol station reservoirs, but the challenge is that they are often underground, which is an issue for regular maintenance, he says.
usually this is why the sensors used in this kind of situation, since they are underground, they put into consideration, of course, that they are going to be buried underground, and as such, maintenance of sensors doesn't come often. It doesn't really come often, of course. So we put into consideration the design of the sensor for specific purposes. Such sensors, like in the fuel station, what you mentioned, that is being buried underground, in some scenarios, they carry it out like there are modern situations whereby they make it possible that you have an external access, although it's always really difficult but when you want to carry it out or take it out, remove it completely. But in the manufacturers, in the case, always have these at the back of their mind during the design, thereby limiting intermittent intervention or for during to limit breakdown. This is a practical part of it, but we cannot avoid completely. We know that
Yeah.
it is very difficult when you want to intervene with it.
Mhm. Thank you, Alfred. Mr. Armando further asks, can the Raspberry be used to mitigate the high acquisition cost of PLC with these sensors?
Can the
Raspberry Pi.
Raspberry Pi?
Yeah.
The efficiency of Raspberry Pi, it's another thing what I can say. However, not really used often as seen, unlike in terms of the PLC. Or if he has, of course, a very nice view on how that can be to mitigate that, that is appreciated. We are a team of engineers, and then you can send also your contribution on what you think about it, and then we can throw this to the OEMs and make suggestion for these designs and publish it. It will be a nice contribution from him. Let's see how we think that can be.
Sure. And Mr. Musa asks, is the 2 out of 3 voting systems applicable to smart sensors also, as found in conventional control systems?
Smart sensor, he's talking about the
2 out
total.
of 3 voting systems applicable to smart sensors, he asks.
Yes, we have a lot of smart sensors. If I may get the question correctly, if asking if 2 out of 3. Am I correct?
Yeah, he says 2 out of 3. Yes.
Uh, 2 of the type of measurement that I discuss about in smart sensors. We, of course, exactly. For example, smart sensors, we have application of smart sensors in pressure measurement. You know, I said in industry, we make mention of, we measure widely 3 types of pressure: gauge and differential pressure, and then level pressure, especially. But in the case of, vacuum pressure, smart sensors are also widely used, like for vacuum measurements, widely used. For example, let me cite as an example, if you, which I'm very much familiar with, like in the filling industry, your filler bowl, it's a rotating machine. In some filling automation, in some filling industry, you have a rotating filler where it is a rotating bowl. On the bowl presently, some manufacturers are now incorporating a smart sensor to checkmate the pressure inside the bowl. We have a counter pressure inside the bowl during filling. So manufacturers are already now incorporating the smart sensors, and these smart sensors talk directly with their controller. As such, during rotation, they limit also this, there is nothing like wire, and then they can checkmate everything, and they are more precise. You can gain access directly to this information from the controller themselves. So they make it more accurate. I don't know if I answered the question correctly.
Yeah, I guess it answers his question, I guess. If not, Mr. Musa, please put in what more you want to know about this. And Vitali asks, which piezoelectric material is most used in pressure sensors currently nowadays? Is scandium aluminum nitrate, or it is not yet in mass production? He asks.
Different OEMs, for example, IFM, we have Omron, we have different type of sensor manufacturers. They decide to they choose what they want. However, from my practical knowledge, I have seen more quartz use, more of quartz use than many others. There are a lot of other ones like Rochelle salts. There is a scientific name for it, but practically known as Rochelle salt, and taumarine also. It's also widely used. I know 3 especially. However, all depends on what the manufacturer might decide to use for the production.
To add on this, does it also like dependent on the cost of the material itself? Like quartz is more abundant and more widely used, but then the other ones needs a little more of fabrication and mass production, I guess, right?
Exactly.
Right. Yeah.
Because they also put into consideration what is also much available in the environment, and that's it. What is also
Right.
easily affordable.
Right. Exactly. I hope that answers your question, Vitali. And Lenin asks, what are the challenges in integrating piezoelectric sensors into existing automated manufacturing systems, particularly in legacy systems that weren't initially designed to accommodate them?
Actually, the challenge is we have to the precision involved. For example, you have to know what type of measurement you want. If you are going to carry out millibar measurements, very tiny and also very high measurements, which require very much more of it. So you have to put into consideration, you have to factor what you want to carry it out, and then know the choice and the displacement material, because there are some materials you're going to use, like I will say like a jacket to house these sensors. If you are using, for example, stainless steel to house quartz, you have to also put into consideration if you are using another type of material to house maybe tourmaline. So these can have effects or disadvantage depending on the choice of material you are using to house the piezoelectric material. So this is, I think, one of the great challenges, personally, what I have seen that pose challenges associated with the choice of piezo material use. Although the manufacturers, they try to eliminate this as much as they can.
Right. And further, Lenin asks a very important question to the students, particularly. Are there any specific hands-on projects or tools you would recommend for students who want to work in sensors in automation, especially in manufacturing systems?
For students who want to work in manufacturing sector, I was
Yeah,
also
yeah.
a student. I started also as a student until present. So I will say from experience, hands-on skill is very important, and also learning from webinars like this ones first. And then there are a lot of information available online and also in practice. However, I always recommend for any students who want to go into the field of automation and study to carry out practical affiliation either with an industry. It could be any industrial sector. It could be even a manufacturing firm, and starting from there. The hands-on skill, it's very much important, as it's going to help you and guide you. You see your theoretical aspect of what you learn, how it is being applied in practice. For example, we have discussed elaborate about pressure sensors application in boilers, in a vacuum pump, and many more. But if you do not work have a hands-on skill on these things, it's a great barrier, believe me. So I will encourage whoever to push away fear for the students and have access to practical affiliation, a hands-on skill, and be very much determined. However, there are also a lot of software you will get yourself used to in terms of automation. You have to learn about programming skills, and there are a lot of programming skills like Siemens programming, and also there are, sorry, a lot of controller type with their programs like Siemens, like Allen Bradley, Omron, Mitsubishi, and whichever. So you look at what's available in your environment, and then you dive much into it. You do much personal study and practice. It will help you more. Of course, most of these software developers, they also incorporate simulations. So you can practically do all this by yourself in your home by regular practice also. It will help you a long way.
Right. Yeah, thank you so much, Alfred. And finally, I have a question that's very basic. What is the key difference between like doing an academic research compared to an industrial research? Like, or how to bridge between these two? Because many of the industrial people, I mean, they do not prefer the academic experts. I mean, basically, that's the fact, and I don't know the reason. And I'm also I'm a like a early career researcher. So, do you have any suggestions or something to do about this?
Um, really nice, and personally I've experienced it myself. One of the challenges associated with academic research and practice in the industry is that when you come down in the industrial sector, you realize some slight differences from what you know theoretically. Let's cite as an example, we know already that the standard for the standard gravity is 9.81, I think, meter per seconds. This is a standard. But when you take a practical measurement, you might realize that it's not up to. But we assume, okay, this is what we draw a conclusion, this should be the standard, and we are, and this is also applicable in different things. I'm only citing that as an example. So in the industry, you realize so much slight difference from practice. This occurs oftentimes. If you go say something and then you look at what is being published from most textbooks, and from practice, you realize there are differences. It's not in all cases, but because of this variation and the academic technologists, I will say some practical engineers from the field might not prefer the academic people, in the sense that they might not be considered to have the real practical knowledge in demand also. But we can bridge this gap. I think one of the things it's how we integrate practice in our schools, how we can integrate what we do in the industry to the academic sector more fully, so that we can bridge this gap. This is a wide gap, and
Right.
and this is affecting even in not only in Africa or Europe, in the Americas, in Asia. I see this a lot. The other day, I was just 2 weeks ago, I was in Afghanistan commissioning a machine, and a technician told me something. He said, "Sorry, this is what I was taught in school." He just newly joined the firm. I said, "Okay, let's see how it goes." And we were doing what we call tuning, auto tuning for a ceramic drive. Unfortunately, we didn't get it accurately like it was in what he knew. And he brought his textbook out, and I told him, "Yes, I know." So I believe that if we can integrate more practical courses in our academics, it can help to bridge the gap between the industrial sector and our theoretical academic practices.
Yes. Yeah. Thank you so much, Alfred. And I think we are almost at the end of our session. Like, it's 4 o'clock here, and I see the participants are literally leaving, and so we'll stop here. I thank Engineer Alfred for his really inspired talk. Like, it gave really valuable insights into sensor technologies and their practical applications in manufacturing industries. It indeed bridged the gap between the academic and the industrial research. So thank you so much, Alfred, and thank you so much all the participants who were in this meeting. I hope this talk was useful to all of you.
Thank you so much, all as well.
Thank you, guys. Yeah, bye.